Let's talk a little bit about the unusual physics of UAP. Now, this is what we get involved with in the hardware factors group. Again, given these things that have been observed and measured, we're not talking one-off metrics here. There are, and I mean, we have multiple dozens of radar signatures that give these kind of views. So one thing you'll see is the extreme accelerations that they go through. In the Nimitz incident in 2004, I think we've all seen on TV and on YouTube about the Tic Tac, right? You'll see the Tic Tac video. This thing again, descended from 28,000 feet to sea level in less than a second, right? Now, that doesn't sound too terribly by itself extreme, right? Okay, it's really good. It just fell from the sky. No, it had to accelerate from the sky to get there in less than a second. If you calculate the G forces involved, 5,000 Gs. That something the size of an F-18 fighter went from 28,000 feet to sea level under 5,000 G of stress. That's incredible. To do that, if you calculate the energy requirements to do that, it's 10 times the nuclear output of the US out of a Tic Tac, the size of a fighter. Now, I don't know what this means, but that's insane amount of energy, right? And think about that. There was no noise. The energy didn't get dissipated. How is this happening, right? It's unusual. So what we have to think about from our group is, if this is a common occurrence, how do we detect something like this? If this energy is going somewhere, how do we do that? We see that they routinely hit hypersonic velocities. Matter of fact, this list, I want to give due credit, came from the Seoul conference, Dr. Kevin Knuth. I gave a YouTube link here. It's very interesting to listen to if you want to listen to it. This is just a summary of his observations, but this is what we use. But we're seeing these things typically hit hypersonic velocities. There was a JAL aircraft who's on radar measured one of these objects in his flight path. They were going from Japan to, I forget, to San Francisco. I might be wrong there, but they were flying over Alaska. And they measured the speed of this object at 270,000 miles an hour at Mach 350. That sounds like it's made up. It has to be a sensor issue, right? There are dozens of these measurements, dozens of them. No sonic boom or plasma trail. You would be ionizing the atmosphere at those speeds, but nothing. So these are things that we would say, okay, what's going on? What can we learn from that? We've recently learned that these objects go through transmedium travel, and it's really kind of a recent development. They move seamlessly between space, air, and water like it's not even there. You don't see any deceleration whenever they enter. The Tic Tac came out of the water and then went right up into suborbital location. Here's one of these things that we're making use of right now. It's number 4. They have high luminosity. They glow for some reason. I don't know why. We're trying to find that out. When you see them in the daytime or the nighttime, they're giving off light. So the key is, can we get some spectrographic analysis of what these are? And I'm leading a project that hopefully will be able to do that. And we'll talk about that shortly. But if you just measure the luminosity in the sky, it comes to about 30,000 megawatts just for the glow. If you look at the spectrum of that light given off, it should be at about 30,000 megawatts just for the light. So they're not hiding. But what is the physics behind something like this? I don't know, but all I'm looking at is there's light. And if there's light, it can be analyzed. So that's what we try to do in the hardware factors team. We do know that they do have strong electromagnetic and magnetic field effects. And at least when cars were under a different technology, they would stall. They would interfere with the starting system. The modern cars, not so much. but there was indications of these strong fields. And what photographs, if you take polarized photographs of these objects, um, you do see this interference pattern indicating a strong magnetic field. The other thing I think I mentioned earlier is there's no observable energy deposition. One of the basic tenets of the universe, right, is the conservation of energy. So if this UAP is going at hypersonic speeds, suddenly comes to a stop, where'd all the energy go? Right, there should have been an explosion. There should have been a rush of air to displace water. I mean, there should have been something, but there's no evidence of this. That tic-tac maneuver, again, and it shows this energy in equivalent to 250 Tomahawk missiles. It's insane what's happening. And then as from a physics viewpoint, you would have to say, okay, there at these speeds, you're starting to introduce, you're not quite there, but you're starting to introduce a few relativistic effects. If you're going at that speed, you're nowhere close to the speed of light, so it's not going to be large. However, I mean, that's still fast enough that you should see differences in clocks. I mean, we do know that just our geosynchronous, or I'm sorry, not geosynchronous, but our GPS satellites have to be time adjusted because of the relativistic effects of being in a gravitational field. So maybe there's a way from measuring time that we can get some idea of what the propulsion system might be. Absence of any known propulsion or control surfaces. These things are all different sizes. They're different shapes. They're orbs. They are tic-tac shape. They look like blobs sometimes. They look like diamonds. There's all kinds of different shapes from these objects. So there's just a recent release on YouTube. There's a team called Skywatcher. They're out and trying to capture some of these events, and they have a nice dictionary or topography of each of these different kinds of craft that they're seeing. Again, no answers. We're starting to look more underwater. There is more and more evidence that there are underwater events. There was a ship in New Zealand that it was on a mission where it would go out, turn around, and then look back with sonar to see if someone was chasing them, right? So I mean, it was a cat and mouse kind of assignment. Well, then they noticed on their sonar, there's an 800-foot object out there, and it's been following them. It's 800 feet long. That's bigger than a submarine. And when they tried to do evasive maneuvers, this thing closed in on them underwater at 3,000 miles an hour. Again, it violates some fundamental, it makes you think twice. Okay, let's say they do develop a technology that you can travel at that speed under the water. The pressure wave should be easily measured, and I'm using sonar. I mean, I'm using sonar to measure its speed, so it's responding to a pressure wave. But why isn't it producing a pressure wave when it comes to me? It's really mysterious. So again, we're trying to evaluate these kind of things to say, okay, what kind of sensor could you deploy underwater that could measure something like this? And then finally, one of the characteristics that we are curious about, there appears to be some kind of behavioral intelligence. We don't know if it's biological in nature, AI in nature. We don't know anything about it, but it seems to know ahead of time when we're searching for it. It was interesting that under Ryan Grace's experience, that this thing went back out to its cap point. Now that's the point at which these aircraft enter the airspace at which they're doing their maneuvers. It knew where it was at. How did it know that? It was not briefed. It's just there seems to be they have a way of finding out things that are mysterious. So these are the things that we look at. again, we're not trying to invent the physics. We're not trying to invent a magnetohydrodynamic drive, even though we have some NASA scientists that are working on those very things, right? So we're leaning on them. Okay, if you're using such a drive, then what would be the detection scheme? And how would you evaluate it? And that's what we want to try. So the scientific implications are real, and this is what we care about. Again, I like anybody else, want to know what it is, but there are bigger impacts to humanity, right? If these power requirements are this large, that's free energy from our perspective. So if we can get an idea of how to measure it, maybe we have a clue for free energies. Structural stress, accelerations of 5 to 10,000 Gs, it shreds anything we have. So maybe Star Trek had it right. There are inertial dampeners out there, right? So there may be some kind of things we can learn from it. Being able just to eliminate sonic booms would be tremendous for travel, right? So that's something we want to know. Missing energy dissipation. Where did all that energy go? Well, then if we knew something like that, what's a mechanism for doing that? It could save lives just in catastrophic events. And of course, there's the unknown physics versus unknown engineering. So the tack that we're taking is that we don't think that there's unknown physics. We think there's unknown engineering. And that's the lens at which we're looking at. Because otherwise, if you're throwing out your physics, you wouldn't know how to measure anything. You've got to assume that at least we have a good idea of what the physics, at least of measurement, what physics are there.